Hello boys and girls. So as you might have noted, I'm in the job seemingly of accumulating all of the ingredients I need to talk about formal set theory, and in this video we are going to talk about the von Neumann model of finite ordinals, or the von Neumann model of natural numbers, if you will. And this relates a little bit back to our talk about the hereditarily finite sets and the von Neumann universes. This is the framework in which I will identify also the natural numbers that I model. If you remember, there was this sequence of sets that starts with the empty set, and then you take the power set more and more, like repeat iteratively, and you get always a bigger universe in this way, like the universe level that is beta plus 1 here, and the universe V with this index is some set that contains more sets. And we will not go, of course, to an infinite variation. I will just in my implementation go to a finite level, but this is the background. I discussed this in that video in much more detail, and I will also make use of the power set operation that I implemented, of course, to actually generate those sets. By the way, subscribe to this channel, of course. And the stuff that I will elaborate on in this video has a few sections on some Wikipedia pages. Not much details, but it has here the set theoretic definition of natural numbers page. And even in the natural numbers Wikipedia article, there is a section on von Neumann ordinals and even semi-low ordinals. Okay, so let's jump into it. So this is again the implementation that I had in the previous videos that I had here. And written in a way that actually makes use of an explicit constant that is the empty set. And here I generate these finite von Neumann universes. So Vi, the 0th level, is the empty set, and then each set is obtained from the previous by taking the power set of what you have so far. I print it out, denote the level, show you the set. The set is of course just a list in my implementation, but it's in one-to-one correspondence. And then the size of the thing. So Python, the file has power pi, and okay, let's actually go to a not so large set. So the 0th level is the empty set. The first level is the set containing the empty set. The second level is this set, and then the third level is this set containing 4 elements. And furthermore, we get to 16, and then as you have just seen, it quite explodes. If I go to the 6th, I get a set that has already, power set of a 16 element set, so thousands of elements. And so this is a little bit like Lisp, a bunch of brackets just, right? And so if you have a set theory that has no elements, that has nothing but sets in it, like the standard Zermelo-Fraenkel set theory has, for example, then if you want to talk about things like numbers in it, then you have to also model the numbers. So you have to represent everything using sets, and the Neumann representation that we are going to talk about here for finite numbers, for natural numbers, is one such model. And it's actually rather straightforward. So let me actually reduce this again. So similar to the Neumann universe, number 0, we say that we identify the number 0 with like the 0 number as set with the empty set. Okay, and what is then done, as you see in this page, for example, so the 0 is represented as the empty set, and then the number 1 is the set containing just the empty set, and then going on, the number 2 is then the set containing all the numbers before, and so on and so forth. So every, like the number 0 is the empty set, and every other finite number, for example, let's say 9, is just the set that has 9 elements in it, namely all numbers from 0 to 8. If you, for example, if you look at, this is also explained here, and it's also explained that from going from one number to the next, what you can do is you just take the number and make the union of this number with the set containing this number. So for example, if you have the number 5, and that means it contains a 5 element set, it contains exactly the numbers 0, 1, 2, 3, 4, and then you take this, everything it contains, and make the union of everything it contains with itself. So the new set contains 0, 1, 2, 3, 4, and also the number 5 that contains all these. Well, then you get a set containing 0, 1, 3, 4, 5, and that happens to be exactly the number 6, right? So you can compute the successor by taking the set and all its elements and adding the set itself to it, and creating a set that has just one more element, namely this here, the set itself. That's in contrast, this is one idea to represent the numbers as sets. Another one would be to do just this. You say, well, the same 0 is the empty set, and then each number is just the set containing this set. So all the difference here is that all numbers always are just singletons that just contain the last number. Right? In this Zermelo ordinals definition, the number 9 would be the set containing just the number 8, and the 8 would be the set containing number 7, and so on and so forth. There are some nice aspects to the Neumann definition. One of them is, for example, that the set of 9 elements, that is the number 9, where there's a correspondence between its size, like directly its size, and the number it represents as we think of it, as a digit. And similarly, I mean, not just for digits, of course, the number 1000 would have 1000 elements, namely everything from 0 to 999. This is one aspect, and also that the comparison, for example, if you want to say that 8 is bigger than 7, then you can test it by checking whether the number 7 is in the number 8, right? Whenever a number is, whenever a number A contains another number B, that means that A is bigger than B, right? So for example, the number 3 is represented by the set containing 0, 1, 2, and so it has the number 1 in it. So we know that 1 is smaller than 3 and not the other way around, for example, because the bigger number that has more elements comes later. Okay, so now that I have explained this, we're going to implement this as code. So 0 is the empty set. Then we can define the successor in a way that I just described. We take x, whatever number this is, and return x plus the singleton x. We make the union of this, this concatenation acts as a union for us. And if I want now to translate the Python number to this sort of implementation, so this is the num will be our set implementation, and the n will be the Python number as you use it normally in programming. Then you say, well, if n is 0, then you return our set 0. Otherwise, return the successor of num of a smaller number, and this is a recursive call here, right? So it will go down till it finds 0, and that's already a very valid implementation. So for example, if I do print the number 4, or let's start with 2, print the number 2, right? So let me do it like this. So Then the number 2 is this thing. It's a set of 2 elements. It holds the 0 and it holds also the number 1, which is the set containing 1. If we're going for, let's actually print both, 2 and 4. Then the first thing that we just had is the number 2, and the second thing is the number 4, which holds 0, 1, 2. This is exactly this, and this is the 3. This is the set containing 0, 1, and 2. Okay, let's go on. So now, as I said before, we can actually write a comparison function, the less function. You know, this is what ordinal numbers is all about. Just by checking whether one set is inside the other one, right? So assuming the input to this function that I'm just writing here, the less function, is just sets that are actually ordinals in this way. Let's say I pass A and B and they are both ordinals. We just have to return whether A is in B, right? And for the sake of things to come, I will call this omega less. So this is the less operation on the set of finite numbers. Omega, I will do a video on more interesting order types, orders on the natural numbers actually, so countable ordinals that are different than this simplest less comparison. So I plan a video to do to implement omega squared comparison, which is going to be very cool. So for example, you know, we might print whether or not the number 2 is smaller than the number 4. And it will say true. And if we go 5, false. Okay, makes sense. And now I'm going to implement a little bit of a hack. So in this video, since I cannot produce arbitrary level of for Neumann universes, where the computation of the power set, especially in my implementation, takes too long, I will now implement a check whether or not a general set that I pass is actually a Neumann ordinal. And of course, I could now, you know, check all, like go into the set and go into the sets of the sets and check whether there are numbers in there and translate them. But I just want to write a one-liner here, and since I just go to a finite size, I will implement this isNum function simply by asking whether or not a set that I pass is among is a natural is a Neumann number to some maximal size, and the size is going to be just, I don't know, 6 or something. So I say, you know, basically I can do this. Return S is smaller than or is in num 6. So this is num doesn't actually do a pattern match that I could implement, but I'm just checking whether or not it's any number from 0 to 5. Let's go with this. Maybe let's go with 7. The point is this, that I will want to use it later, and if I do a complicated implementation where I go into every set, then it just takes forever, and I don't want to sit out and wait. This here's a little bit of a hack. And finally, I also want to do the inverse of num, which is very easy. So from num, given a num, I already elaborated that I just have to return the size, right? But because the size actually corresponds directly to the digit or to the number, and so if I return the length, then Python will just compute the corresponding number for me. Yeah. So and the last thing that is to do is I have to write the function that, you know, if you look at this universe level 4. Then this is like a little bit ugly, and I'm interested in what kind of sets do I actually have there, assuming I use the Neumann identification of natural numbers for the set universe I'm constructing, right? And so what I have to do is I have to go into the set, and for example, I will translate this set here into the number 0, and then I will search, is the number 1 there, is the number 2 there, and so on and so forth. I have to do this also recursively. So in a very functional programming kind of fashion, I will now implement a generic function that creates a recursive function that goes into a set and goes deep into the set, and it will look like this. So I will call this rec for recursive, and this will do a cast. The cast is going to be from num, so I translate these set expressions to the normal Python things that I have. But I can also, of course, only do this on things that are actually numbers, and so I also have to pass a check. That's going to be isNum. And here I will define a function f that does actually this thing and has a recursive aspect to it, which will return something, and then the result of this rec function will be this f exactly. Okay, so what do I have to return here? Well, if I will return the casted version of the set if this is actually, the check is valid, and otherwise comes the recursive aspect. I will map f on s, so I go into the set deeper and apply this again, and so on. This way I also can go deeper and deeper into the set and do all these translations of sets to whatever model I pass, right? This cast could be anything. In this case, it's the Neumann numbers. Also, just for the sake of the video here, I will sort actually these sets. So the only point of this is that I have I group together similar looking objects. In particular, I will have all the normal numbers at the beginning. Okay, and we are pretty much done. So let me give you an example. Let's say I have some set. So that contains maybe, the number 5 as list, and maybe this object, which happens to be the number 1. But also, like, let's say some other strange object, let's say this thing, and that might also have this set, so maybe this set, and also the number, let's say the number 2 and number 4. So might well be that I did syntax error now, but let's try. So I print out this recursive call on some set, and the recursive call is going to be with from num and isNum. So this is going to be my f that does this recursive operation and apply to this. So let's check it out, and actually let's print this out. So okay, syntax error here. Okay, so he took this set and translated everything he could to the normal numbers in Python, right? So I have the number 2 and 4 and 5 explicitly in there, so there's no surprise there. He recognized that this is actually the number 1, and then there's this strange set, and he recognized that this is actually the number 2. It's a set containing 0 and 1, and this is nothing really, apart from the fact that this is the number 0, this is the number 1, so he results in a set containing a set containing a set containing the 1. See, this is the implementation that works. Okay, so here I already compute the 4th level, and this vi will survive till the end of the file, so I can just do this, and he will translate now this strange set and try to identify all the Neumann ordinals here. So let's do this. So he will see everything he finds there. So the 4th Neumann universe level holds the first 4 numbers, and also holds a bunch of other sets. And it is actually not surprising that that these are in there, the first four, because the construction of the universe is taking the power set operation. So everything, it unpacks basically all possible subsets, and of course if I take the empty set and take the power set, actually get here, and then once I have the set containing 2, then there's not much to do to get to 3, right? I just have to put 2 together with everything else, and this is all part of the power set. So successively all these Neumann numbers appear also in the Neumann universes, but then a bunch of other stuff. And the Neumann numbers are not the only thing that has a model. For example, the normal pair of things, like the ordered pair, has a model. And if we went on and generate more bigger universe levels and define an implementation with my recursive abstract function, I could also identify pairs of numbers. So I could search for at which universe level does the pair containing the number 2 and the number 6, the 2-element pair, pop up, and so forth. And so you see how suddenly numbers arrive in these universe levels. But also the interesting thing is, of course, I have to go to infinite universe levels to get all the numbers in there. So clearly the set of natural numbers is not in any of these hereditary finite generated sets that I get with the power set operation. And indeed, just using the power set operation, I cannot get away from finite sets to an infinite set. This is like a large cardinal jump. But I will talk about this in later videos. So I guess you have now seen how at least the finite ordinals work out, and how an order is easily defined there. And in some future videos I will talk about much more interesting orders, like that a little bit harder to define, before I go and talk about uncountable objects. So thanks for watching. Subscribe to this video. Tell me what you want to hear more about. I already heard that I should make more videos on Idris, and for these things, for Idris, of course, if I talk about it, then the implementations are a little bit more intricate than just Python scripting. So that's why it needs more preparation. But I will definitely come back to that as well. So thanks for the suggestion, and good night.